Welcome everyone to the final part of our text generation project. In this part, we're going to load up the model, but we'll only load the weights. That way when we build the model, we can actually build it to accept a batch size of 1. And then we'll create a function that can generate text given the model. Let's get started and continue where we left off last time. Alright, in order to actually load up our model or load up your model that you just trained, first off, make sure you've saved your model. So if you decided to actually train your own model, go ahead and save it. And then the next step, to load it up so it has a batch size of 1, create a new model. We'll say create model, and then pass in everything we passed in before. Vocab size, embed size as embed dimensions, and then RNN neurons. But finally, for batch size, say batch size is equal to 1. So you'll create a model with batch size equal to 1, and then say model load weights, and then pass in the actual file that you saved or our file, which was Shakespeare_gen.h5. And then after that, we'll say model build, and we'll build it passing in the input shape. And the input shape stems from tf tensor shape, and then we'll say 1 by none. So running these 3 lines of code here of creating a new instance of the model where batch size is equal to 1, and instead of actually loading up the full model, we will say load weights, and then we will build out the model with that particular shape size. Okay, so now when I say model summary, same model as before, but notice instead of 128 as the batch size, it expects just 1. So that means I can create a function that will be able to generate text. So the way it's going to work is we'll say df generate text function. It's going to take in the model. It's going to take in some starting seed, and then it will take a gen size argument, essentially how many characters we want to generate. Let's go ahead and generate 500 characters by default. And then we'll also specify a temperature argument that you can play around with. We'll set it to a default of 1.0. So the basic idea behind this function is to take in some seed text, format it so that it's in the correct shape for our network, and then loop the sequence as we keep adding our own predicted characters. Very similar to the work we did in our time series problem with recurrent neural networks. So what we'll do here is we'll say the number to generate is equal to the gen size. So this is the number of characters to generate. And then we're going to start by vectorizing the starting seed text. So this start seed will actually just be a raw string that the user can pass in. So in order to do the actual evaluation, we'll say input evaluation is equal to character to index s for s in start seed. Essentially, for every character, we'll go ahead and transform it to an index, and then we'll have a list of those. And then we want to expand this to match the batch format shape. So we'll say input eval is equal to tf expand dimensions, where we'll say input eval, comma 0. So that expands the dimension so that it's in the correct shape, and then we're going to create finally an empty list called text generated, which is going to hold our resulting generated text. Then finally, we can specify a temperature, so we can say temperature is equal to temp, and the temperature is a value you can play around with. You can make it lower or higher depending on basically how random or more surprising you want the results to be. So we'll show you in a second in our loop how that actually comes into play when generating the predictions. For right now, we'll go ahead and reset the states of the model. So we'll say model reset states. And then what we're going to do here is say for I in range, the number to generate. We'll first generate some predictions. So we'll say predictions is equal to model and pass in that input eval that we just created. And then we'll say predictions, and we'll remove the batch shape dimension. We can do this by simply saying tf squeeze predictions 0. It's almost essentially reversing the tf shaping we used earlier. That is to say, this tf expand dimensions. It's the opposite of squeezing them. And then we want to use a categorical distribution to select the next character. So, whoops, make sure we spell predictions right here. Perfect. Then we'll say off of this predictions is equal to predictions divided by temperature. And then we'll say the predicted index or predicted ID is equal to, just as we did before, tf random dot categorical predictions. And we only need one of these characters, so we'll say samples is 1. And then finally, because of the format this is returned in, we'll do a little bit of indexing by saying -1, 0 to numpy. And essentially just indexing formatting so we get the actual single ID, which means then our input eval will say tf, we'll expand the dimensions back out. So we'll say expand dimensions. Notice the braces there to predicted ID, comma 0, and then we'll transform this back to the character letter by saying text generated dot append index to character of the predicted ID. Once that's all done, we'll go ahead and make sure you check your indentation here. We'll return start seed plus, and then we'll join all the items together. We'll say join the text generated list. All right, so let's go ahead and make sure we understand this. We take in the model, the starting seed string, the number of characters we want to generate, as well as the temperature. Then we assign some variables here, number to generate, as well as the temperature, and then we're going to get our input evaluation, essentially transforming that string back into the index locations. We'll expand this dimension so it's in the right shape for our model. We'll reset the states, and then for I and range number generated, so for each of these characters, we'll get a prediction. We'll do squeezing to essentially undo this expand dimensions in order to actually grab the predictions. These are what these two lines are doing. We can affect the actual probability of those distributions based off of temperature. You can play around with that value. 1.0, essentially the base, essentially no adjustment, since dividing by 1 is the same as leaving it the same. Then we get predicted ID, tf random categorical. It's actually grabbing it, a little bit of indexing here to convert it to numpy so that we get that single digit, expand it back out so you can get the input eval shifted forward by your predicted text, and then we get this text generated and we start appending it. Okay, so let's run this, make sure we didn't commit any typos, and we'll go ahead and say print, generate text, pass in our model, go ahead and pass in anything that seems like it should belong in a play by William Shakespeare, such as Juliet in all caps, and then let's go ahead and say our gen size is equal to 1,000 characters. Run that, and this should take a little bit of time, but eventually you should see something that hopefully looks Shakespearean in its output. Okay, so here is what it came up with. You can see Juliet, and then it accidentally started going in all caps, but again, it's doing this character by character. But you can see King Richard, how now mistress Desdemona, help me pluck over to proud, no doubt us. And you can see some of these are actually just kind of made up words, but other ones actually make a lot of sense. So you notice it's doing a couple of typos here, but on a character by character basis, it's pretty amazing that it's able to start labeling scenes, and after a scene is labeled, it tells what characters are entering, and then it really learned the structure of you have some character name in all caps, and then what they say, then another character name in all caps, and then what they say, etc. So pretty amazing work that just on a character by character basis, this is able to learn the structure of Shakespeare. Okay, definitely check out the rest of the resource links for more examples of this sort of recurrent neural network architecture being used to generate results. Thanks, and we'll see you at the next section.